Imagine, let's make a bold assumption. One day you push open a door and walk into an incredibly vast banquet hall. The hall is filled with billions of tables. Every table is set with a tablecloth, exquisite cutlery, the wine is poured, and the food has just been served, still steaming. What does this mean? It means the banquet is about to begin, or it has already begun. But you look around, and the entire hall is in dead silence. There isn't a single guest. This empty banquet hall is our universe. And you, standing at the door wondering where is everyone, our humanity. The big question we're exploring this time is, do aliens exist? Now, some people who hear this topic might think, oh, isn't this just the Fermi Paradox? This topic has been talked to death. The three-body problem won its award 10 years ago, and you're still stuck on the dark forest? Friends familiar with our show know that this little program isn't a science pop or philosophy pop show. It's a show where we all come together for a meeting to discuss big questions. Today, we're not going to popularize what the Fermi Paradox is, everyone already knows. Today, we're going to sit down together and earnestly try to solve the Fermi Paradox. As we said, every participant today is like a detective. Let's use our collective intelligence to crack this cold case, the Fermi Paradox. Before we start the investigation, we still need to introduce the case file. As I said, we won't re-explain the paradox. Instead, we'll use a hardcore logical analysis to break down how the Fermi Paradox even became a paradox. The Fermi Paradox is a paradox because two propositions, which we both believe to be true, exist simultaneously but contradict each other. Proposition 1 is, we should have found aliens. Proposition 2 is, we have not found aliens. Proposition 2 is a fact. Proposition 1 is a high-confidence deduction. This deduction is derived from two premises that we widely believe to be true. So, premise 1 plus premise 2 equals proposition 1. But only one of proposition 1 and proposition 2 can be true, yet they both appear to be true. Thus, a paradox emerges. That's the entire logic of the Fermi Paradox. But let's explain this hardcore logic, or it'll be too dry and confusing. First, let's explain the two premises of proposition 1. From premise 1, the principle of mediocrity, we can deduce with near certainty that alien civilizations exist. From premise 2, civilizations inevitably expand outward, we can deduce with near certainty that we should be able to find alien civilizations. So, what is the principle of mediocrity? It's also known as the Copernican principle. It says that humanity is not the center of the universe. We are not the chosen ones. We were not appointed. We evolved according to the fundamental laws. Right? We, like all things, must obey the simple mathematics and physics of this universe. We are not fundamentally superior to anything else. Therefore, according to these fundamental laws, since the universe could evolve human civilization, it theoretically can evolve other alien civilizations. Of course, the evolution of intelligent civilization is a low-probability event, right? It requires a stable, burning star, a planet in the habitable zone, an atmosphere, water, and so on. But, no matter how small the probability, if the sample size is large enough, it becomes a near certainty. It's like winning the lottery. It's a low-probability event, right? But if you'd been buying a ticket every single day for the 13.8 billion years since the universe began, your winning the jackpot would be a near certainty. And as we all know, our universe is so vast, its sample size is simply astronomical. Astronomical in the literal sense. So, let's look at our special planet Earth through the lens of the universe's 13.8 billion light-year spatial scale and 13.8 billion year temporal scale, and see just how mediocre it is in this massive sample. Okay, let's look at the spatial scale. We don't even need to look at the whole visible universe, let's just talk about the Milky Way. It's currently accepted that there are about 200 to 500 billion stars in the Milky Way. Let's be conservative and say 100 billion. Among these 100 billion stars, scientists estimate that 5% to 20% are similar to our Sun in mass, temperature, and luminosity. Let's be conservative again and not use 5% or 20%, but just 1%. 100 billion times 1% equals 1 billion. This means there are at least 1 billion Sun-like stars in the Milky Way. Now, among these 1 billion stars, scientists estimate 20% to 50% have planets similar to Earth, at a suitable distance, with a suitable temperature, and with liquid water. Again, let's be conservative and take just 1%. 1 billion times 1% equals 10 million. This means there are at least 10 million planets in the Milky Way suitable for life. Okay, remember that number, 10 million. Having covered the spatial scale, let's talk about the temporal scale. Evolving intelligent life takes a long time, right? Earth itself took 800 million years for life to appear, and another 3.8 billion years to evolve intelligent life. Alright, we'll give you plenty of time. From those 10 million Earth-like planets we just calculated, let's pick out the ones that are even older than Earth. We know Earth is a relatively young planet in the Milky Way, at only 4.6 billion years old. The Milky Way itself is nearly 13 billion years old. The majority of planets in the Milky Way are older than Earth. Let's not even say majority, let's stick to our conservative 1%. 10 million times 1% equals 100,000. This means there are at least 100,000 different intelligent alien civilizations in the Milky Way. And these 100,000 civilizations have had anywhere from tens of thousands to billions of years more development time than Earth. Think about it. Humanity only had its scientific revolution 200 years ago. 200 years, and we have this technological explosion. Civilizations that have had millions of years of a head start? Things like radio, or galaxy-spanning spaceships, that would be child's play for them. Okay, that's premise 1. From it, we deduce that the existence of alien civilizations is a near certainty. And honestly, most scientists firmly believe this. The universe is this big, how could we possibly be the only intelligent civilization? Right? The key question is, can we find them? This brings us to premise 2. Premise 2 tells us that we must find them. Why? Because scientists generally believe that as an intelligent civilization develops, it will inevitably expand outward and conduct interstellar colonization. Note, this isn't just crudely comparing aliens to humans, saying they must be like Homo sapiens who expanded from Africa to Eurasia, then from Europe to the Americas, and now Elon Musk wants to colonize Mars. Aliens could have a completely different way of life. But no matter their way of life, their underlying logic must be constrained by the universally applicable laws of thermodynamics. This means their survival and development require energy. And the energy of any planet, or even any star system, is finite. When you develop to a certain stage, you must expand outward to gather more energy. Right? Human civilization is only 10,000 years old, and Musk is already planning to colonize Mars. So what about those alien civilizations that are millions of years old? They should have utilized the entire Milky Way by now. The Soviet astronomer Nikolai Kardashev classified civilizations into 3 types based on their energy use. A Type 1 civilization can use all the energy of its home planet. According to the astronomer Carl Sagan, humanity is currently about a Type 0.7 civilization. A Type 2 civilization can harness all the energy of its parent star. A typical method would be using a Dyson sphere. You all know what that is, encapsulating the star to use its energy to the maximum. A Type 3 civilization can use the energy of its entire galaxy. For us, that would be the entire Milky Way. Of course, what a Type 3 civilization looks like is beyond our comprehension. But if we follow the underlying logic of energy utilization, as a civilization develops, it must evolve the capability to harness the energy of an entire galaxy. According to the physicist Michio Kaku, humanity will reach Type 1 in about 100 to 200 years, Type 2 in a few thousand years, and Type 3 in 100,000 to 1 million years. Okay, that's premise 2. As a civilization develops, its increased energy use means it must expand outward and colonize. So what are the methods of expansion? We mentioned Type 2 building a Dyson sphere. Besides that, alien civilizations might develop generation ships. They might also develop self-replicating AI. If they are very capable, they might even visit Earth directly. If they're not quite that capable, they would at least send out radio signals to communicate, right? Let's quickly explain generation ships and self-replicating AI. For interstellar travel, because the scale of space is so vast, the ship must be very fast. For example, at least 5% of the speed of light. If the journey is still very long, say, thousands or tens of thousands of years, you can use a generation ship, also called a space ark. This means the astronauts make their home on the ship. They have children on the ship, those children grow up and have children, and so on, generation after generation. When they arrive at the destination thousands of years later, there will still be living, breathing colonists disembarking to start colonization. Of course, you could also freeze embryos on the ship and have AI raise and preserve them, like in the movie Alien, Covenant. Upon arrival, the embryos are incubated, and they get on with their business. If you think even that is too costly, you can fully automate it. Have AI be the pioneers. This is the idea of the self-replicating spacecraft, first proposed by the mathematician von Neumann. The method is a leapfrogging strategy. The colonizers send AI to a nearby star system. The AI lands, uses local resources to replicate itself, builds new AI spacecraft, and without stopping, launches from that system to the next. In this way, they spread out in a web-like pattern across the galaxy. If the AI ship can travel at 5% the speed of light, it could colonize the entire Milky Way in about 4 million years. A reminder, 4 million years sounds long, but on the 13 billion year timescale of the Milky Way, it's a very short time. Okay, let's review. From premise 1, we deduced there are at least 100,000 intelligent alien civilizations in the Milky Way, all far older than us. From premise 2, civilizations must expand. Right? These 100,000 civilizations should have filled the Milky Way with Dyson spheres and spaceships long ago. But proposition 2 tells us, as of November 15, 2025, there is no reliable evidence of alien existence. Not only have no alien civilizations visited Earth, but our telescopes have also not observed any signs of alien civilizations, like Dyson spheres or spaceships. We haven't even received any radio signals from them. The universe we observe is completely silent. Scientists call this proposition 2 the Great Silence. This is the Fermi Paradox. I said I wouldn't popularize it, but we still spent a lot of time explaining it. This was all to clarify the case file, to prepare for our investigation. Now, before we crack the case, let's introduce the methods. We said the paradox is 2 contradictory propositions. To solve it, the logic is simple, either proposition 1 is false, or proposition 2 is false. If proposition 1 is false, it means either premise 1 is false or premise 2 is false. This gives us 3 main possibilities for solving the paradox. The first possibility is that proposition 1 is true, we should have found them, but proposition 2 is false, we actually have found them. This is further divided into 4 scenarios. We already have evidence of their visit, they are secretly contacting a select few humans, they are quietly observing us, or we are the aliens. The second possibility is that proposition 2 is true, we haven't found them, but alien civilizations do exist. This means premise 2 of proposition 1 is false. That is, aliens don't expand outward, so they can't contact us, and we can't find them. This is divided into 3 scenarios. They can't come, they lack the ability, they can come, but deliberately don't, and they have no need to come. The third possibility is that proposition 2 is true, we haven't found them, and premise 1, the principle of mediocrity, is false. Why haven't we found aliens? Because there are no other alien civilizations in the entire universe. We are the only one. This also resolves the paradox. This is divided into 2 scenarios, a strong rejection and a weak rejection of the principle of mediocrity. Based on these 3 possibilities and 9 scenarios, 13 hypotheses emerge. These are the specific solutions to the Fermi paradox. The main goal of our show today is to introduce these 13 hypotheses one by one. You are the detectives. Each hypothesis is a suspect. You get to judge which hypothesis is the most reasonable solution. So, how do we determine if a hypothesis is more reasonable? Generally, there are 5 criteria for judging a hypothesis's validity. First, consistency. This is the most basic requirement. Your hypothesis can't have bugs. It must be self-consistent and logical. Right? And it must be able to explain the factual material it's trying to explain. You can't have the facts themselves falsify your hypothesis from the start. Second, scope. This means your hypothesis can explain more facts. A hypothesis that explains more is more reasonable than one that explains less. Third, Falsifiability. This means your hypothesis can't be evasive. You can't just state something untestable. For example, aliens exist in another dimension we can't access. You'd be correct no matter what, but it's a useless truth. Fourth, simplicity. This is what we often call Occam's razor. To explain something, the hypothesis that uses fewer assumptions is more reasonable than one that uses more. It's more efficient. Fifth, conservatism. The hypothesis you propose should align with other hypotheses we accept, especially with our existing common sense. You shouldn't propose a wild, sci-fi explanation just to solve one problem, when a less bizarre explanation will do. Of course, it must be said, there's no fixed algorithm for which of these criteria is more important, what their weights are, or which are necessary. This is why people who pull out Occam's razor every time they hear something, well, Occam's razor isn't a silver bullet. It doesn't apply to every hypothesis. There is no fixed algorithm for judging reasonableness. This is why AI cannot replace humans in scientific research. Determining which hypothesis is more reasonable requires human practical wisdom. And this is where we need you to use your intelligence for the rest of the show. Who is the culprit? We will select the most reasonable solution to the Fermi Paradox from these 13 suspects. Okay, having introduced the case file and the methods, let's formally begin introducing the suspects. First, let's look at the first possibility: aliens exist and have already contacted us. The first hypothesis here is that we already have evidence of their contact. Let's temporarily call this the UFO hypothesis. UFOs are often used as proof that aliens have visited Earth, right? We often hear so-and-so took a photo or video of a UFO, claiming it's proof. Of course, many of these are just misidentified natural phenomena. But there are some UFO images that, to this day, cannot be explained by natural phenomena. For example, in April 2020, the US Pentagon confirmed that 3 UFO videos leaked online were authentic and filmed by the US Navy. The aerial maneuvers performed by the objects in these videos are impossible for any known human aircraft. Separately, some people say that certain unnatural wonders on Earth, like the pyramids, Stonehenge, or the periodic appearance of crop circles, are definitely not man-made and must be the work of aliens. If you think those claims have a pseudoscience flavor, well, some scientists have also proposed evidence of alien civilizations. For example, in 2017, astronomers observed an object from outside our solar system passing through. They named it Oumuamua. Oumuamua is the first known interstellar object to pass through our solar system. Its movement was very strange, it was tumbling. Furthermore, Professor Avi Loeb, the chair of Harvard's astronomy department, analyzed Oumuamua's trajectory and found that, besides being affected by the sun's gravity, it had its own thrust. We all know comets have their own thrust, from the reaction force of gas evaporating. That's why comets have long tails. But our telescopes observed no tail on Oumuamua, not even any sign of rocket propulsion. Based on this, Professor Loeb concluded that Oumuamua was an alien ship propelled by a light sail. A light sail is a future technology that humans haven't fully mastered but is theoretically possible. A craft with a light sail could theoretically reach half the speed of light. It needs no fuel, using the sun's radiation pressure for thrust. That's why we wouldn't see any propulsion trail. This is why Loeb believes Oumuamua was a light sail-propelled alien ship. Also, it's not entirely true that we've never received any signals. Scientists have actually received some signals from outer space that are very difficult to explain as natural. For instance, the WOW signal. The WOW signal was a very strong, narrowband radio signal received on August 16, 1977, by American astronomer Jerry Eman. It came from the direction of the constellation Sagittarius. When Eman saw the signal, he circled it on the data printout and excitedly wrote next to it, "Don't answer." "Oh, no, wait." He excitedly wrote WOW. To this day, scientists cannot fully explain the mechanism of the WOW signal using natural phenomena. So, some speculate it was sent by an alien civilization. Furthermore, scientists still can't explain the mechanism of fast radio bursts, FRBs. What are FRBs? They are a high-energy astrophysical phenomenon. A sudden, intense burst of radio waves comes from a specific direction in the sky, lasting only a few milliseconds, but releasing as much energy as the sun does in 10 years. Some scientists believe these FRBs come from a highly advanced alien civilization. Maybe it's a signal they're deliberately sending, or maybe it's the result of a high-energy event, like a war between alien civilizations. In summary, the UFO hypothesis says that Proposition 2 is false. We already have some evidence of alien civilizations. It's just that most people don't take this evidence seriously and still think we haven't found aliens. Of course, critics of this hypothesis say that this so-called evidence isn't strong enough. It doesn't conclusively prove the existence of aliens. So, do you think this hypothesis is reasonable? Okay, after the UFO hypothesis, let's introduce the next one, the lizard people hypothesis. This hypothesis says that aliens are already in contact with us, just secretly, and only with a small number of humans. Think about it, alien-human contact. What kind of high-level meeting would that be? Not just an international summit, but an interstellar summit. Is that something we common folk would be allowed to know? In reality, the leaders of all nations, or at least the major ones, are already in contact with aliens. It's just not broadcast on CNN. That's the conservative version. The more extravagant version says that aliens have already come to Earth and have never left. In fact, some of the most important people on Earth, world leaders, tech billionaires, superstars, are actually aliens in disguise. The aliens must personally play these important roles to control, or at least influence, human civilization. Right? Isn't there a theory that many important people are actually lizard people? These lizard people are a type of alien. They don't look human, but they wear human disguises. They're all aliens. Of course, lizard people is the extravagant version. But the conservative version of this hypothesis is that important people on Earth are already in contact with aliens. It's just that we, the common people, don't know about this interstellar hotline. That's why we think Proposition 2 is true, when it's actually false. Alright, after the lizard people hypothesis, let's introduce the next one, the zoo hypothesis. The zoo hypothesis, says that aliens have already found us, and may have even visited Earth. But they are quietly observing us, without letting us detect their presence. Why observe us quietly? Because their civilization is just so much more advanced than ours. Right? We said earlier, they might be millions of years ahead of us. To them, we are like primitive little animals. If they tried to communicate with us directly, asking us high-level questions, we would just answer, I don't know. Right? So, it's better to just not disturb us and observe quietly. And because they are so much more advanced, they have the technology to observe us in every way without being detected. To them, we are like bugs. A biologist might be very interested in bugs. For instance, how bees use dance to communicate, or how ants move their colonies. But if the biologist tried to interview the bugs couldn't answer. So, the biologist just needs to keep a distance and observe quietly. This also prevents panic among the bugs and allows for the collection of the most native information. So, alien civilizations are observing us, just like biologists observing bugs. This is the zoo hypothesis. Of course, there's another, similar one called the planetarium hypothesis. Logically, these hypotheses have no flaws, they are consistent. But critics say they are not falsifiable. Right? If you say aliens are observing us in a way that is impossible for us to detect, then we can never find evidence to test it. Furthermore, these hypotheses are a bit human-centric. They assume we're so special that we're worth observing. You know, there's a spotlight effect in psychology, where you always feel like everyone is watching you, when in reality, no one is. Right? It's like, even when I'm home alone, I always feel like my goddess is silently watching my every move. So, even when I'm alone, I can't do anything unhealthy. Right? Okay, after the zoo hypothesis, let's introduce the panspermia hypothesis. The panspermia hypothesis, panspermia, also argues that Proposition 2 is false. It's not that we haven't found aliens. It's that we are the aliens. How so? Well, our scientists still don't know how life on Earth began. There are many different, competing hypotheses. One of them is that life on Earth was originally seeded from space. For example, it was spread to Earth via meteorites. This is called panspermia. Life can drift through space on meteorites, like a message in a bottle. Whichever planet it drifts to, if that planet is habitable, life will take root and flourish. Our life on Earth may have started this way. There's a theory that Mars clearly shows signs of past life. Scientists' probes have found traces of riverbeds and canyons, evidence that Mars once had liquid water. And early Mars had more oxygen than Earth, making it more favorable for life. It's possible life existed on Mars, but then, due to geological changes, it went extinct. But a small part of that life hitched a ride on a meteorite and flew from Mars to Earth. And indeed, scientists have found that many meteorites that have fallen to Earth did come from Mars. This is like saying life originated on Mars but developed and thrived on Earth. Mars is desolate now, but that Martian life successfully invaded and took over Earth. The barren Mars of today could be considered the ancestral homeland of Earth's civilization. Of course, you might think the probability of life surviving on a drifting meteorite is too low, what with cosmic radiation and the fiery entry into Earth's atmosphere. Well, there's another version, directed panspermia. This says that life was indeed sent to Earth from space, but it was sent on purpose. Don't think this is some crackpot theory. Its proponents include Francis Crick, who won the Nobel Prize for discovering the double helix structure of DNA, and Leslie Orgel, one of the pioneers of the RNA world hypothesis. They proposed that a highly advanced, intelligent alien civilization deliberately seeded Earth with the spark of life. And since it was deliberate, they could use technology to protect it from radiation and atmospheric entry, ensuring it was safely delivered. Our life on Earth might be part of some advanced civilization's cosmic drifter project. Their robots, in spaceships, fly around planting the seeds of life. We are the product of their project. Therefore, Proposition 2 of the Fermi Paradox is false. It's not that we haven't found aliens. We are the aliens. It's like looking through a telescope at space for years, searching for aliens, only to realize, oh crap, I'm the alien. Something like that. Of course, a criticism of this hypothesis is that its scope is a bit weak. It might resolve the paradox, but it doesn't explain why, besides us originating from elsewhere, we still haven't received any other signals from alien civilizations after all this time. Right? So, do you think the panspermia hypothesis is reasonable? Okay, after panspermia, let's introduce the too-far hypothesis. The hypotheses we've covered so far belong to the first possibility, they exist and have been here. That is, Proposition 1 is true, and Proposition 2 is false. Now, we move to the second possibility, they exist, but haven't come. This means Proposition 2 is true, we really haven't contacted them, but Premise 2 of Proposition 1 is false. Aliens exist, but for various reasons, they haven't been able to contact us. The next 7 hypotheses we'll discuss focus on explaining why aliens haven't contacted us. The first reason, of course, is they can't come, they lack the ability. Why do they lack the ability? The most direct reason is, they are too far away. As you know, the universe is vast and incredibly empty. Traveling from one star system to another means covering a distance of at least several hundred light years. What does that mean? With our current technology, it would take millions of years to reach a destination. Even if an alien civilization is more advanced, they can't travel faster than light. The speed of light is a fundamental limit of the universe. Aliens have to obey the basic laws, too. So, even if their technology is more advanced, say, they can travel at 5% the speed of light, a journey of several hundred light years would still take tens of thousands of years. And that's assuming they've already evolved for a long time to develop that 5% light speed capability. The time required would be even greater. Even if we assume they are so advanced that it only takes a few thousand years to cross that distance, there are humanitarian risks. We mentioned generation ships, where you can have children en route. But think about it, what civilization is willing to sacrifice dozens of generations to fly toward an unknown world? Even with hibernation technology, where you sleep through the long journey, it means this generation of explorers says goodbye to their home planet and their families forever. After thousands of years of travel, when they arrive, will their home civilization even still exist? Is any civilization willing to make such a costly exploration? So, because interstellar colonization takes so long and comes at such a high humanitarian cost, the price is just too high. It's very likely that aliens just decided it's not worth it. And, let's take it one step further. Even if there's a brave alien civilization determined to colonize, say, they fly near our solar system, it still comes back to what we said at the beginning: the universe is too vast and too empty. Whether they come in person or just send a message, it takes too much time to get here. Human civilization is very young. Why haven't we found them? The reason is simple: we just haven't waited long enough. Right? Think about it. Homo sapiens has only been around for 200,000 years. Written civilization, 10,000 years. Industrial civilization, 200 years. We only figured out we could send radio waves into space in the last 100 years. You see these numbers, 200,000 years, 10,000 years, and they seem long. But on a cosmic scale, they are the blink of an eye. It's perfectly normal that we haven't found any trace of aliens in this blink. Just wait. Maybe wait another 100,000 years, and we'll get a hello from them. Right? So, because the universe is too vast and empty, even if civilizations exist, they are too far apart. This explains proposition 2, why we haven't found them. Okay, after the too far hypothesis, let's introduce another can't come, lack the ability hypothesis, the great filter hypothesis. The great filter hypothesis says that, while premise 1, principle of mediocrity, is correct, the universe should be able to evolve intelligent civilizations, even ones capable of colonization. The reason we haven't found any is that there are great filters. These filters are hurdles that stand between a civilization and the ability to colonize the stars. And these filters wipe out civilizations before they can reach that stage. The originator of this hypothesis is the economist Robin Hanson. He proposed 9 great filters. This means, on the way to the 9th level, interstellar colonization, many alien civilizations fail to pass these filters and either get wiped out or, at least, stagnate at an early stage. That's why we can't find them. Never mind the others, just origin of life is a great filter. We've said it before, scientists still have no idea how life on Earth actually began. Because it's just so difficult, so improbable. That's why some scientists suggest it must have come from space. Furthermore, even if life evolves on a planet, will it necessarily evolve into intelligent life? Not at all. There are great filters in the way. Speaking of which, we have to address a common misunderstanding of evolution. Many people think that, given enough time, life will inevitably evolve into intelligent life. And given more time, that intelligent life will inevitably progress towards Type 2 or Type 3 civilizations. As if evolution has a necessary trend, from simple to complex, from low to high. But who says evolution must produce complex, intelligent life? The appearance of intelligent life is not a historical necessity. Evolution has no inherent direction from low to high. Take life on Earth as an example. 99% of all species that have ever existed on Earth are extinct. The most abundant life forms on Earth today are single-celled organisms, like bacteria. Even if we don't talk about bacteria, just multicellular animals, the most numerous animals on Earth are insects. The appearance of an intelligent life form like us is a pure accident. It's the low probability combination of a series of coincidences. For example, 65 million years ago, an asteroid hit the Earth and wiped out the dinosaurs, making room for our mammal ancestors. Or 70,000 years ago, a brief climate change made East Africa relatively humid, allowing our Homo sapiens ancestors to successfully migrate out of Africa. According to Hanson's 9 filters, humanity has been very lucky. We have already passed the first 8 great filters and are currently at level 8. But don't get too happy. We could very well be filtered out by this 9th filter. We could be stuck at level 8 forever, and our civilization could go extinct before we ever gain the ability to colonize the stars. Remember, our civilization is so short. 200,000 years as a species, 10,000 years as a civilization. On a cosmic scale, these are just blinks. Maybe in another 10,000 or 20,000 years, a massive geological climate shift, a supervirus, or another asteroid impact will wipe humanity out before we reach level 9. And since evolution has no necessary upward trend, there's another possibility. Maybe aliens did evolve intelligence, but then they devolved. Their intelligence vanished. Devolved is in quotes, because evolution doesn't care about progress or regress, only survival. In some ways, intelligence is a bad bargain. Look at humans. Our brain is about 2% of our body weight but uses 20% of our energy. Thinking burns a lot of power. It's possible that one day, the environment will change, making it so that we can survive perfectly well without thinking. Or even, not thinking is better for survival than thinking. Then intelligence would be useless for survival and reproduction. Right? Do people who think deep thoughts have more kids than people who don't? Right, many viewers of this show are single. But the people who just eat, drink, and don't worry about anything seem to have more kids. You can imagine a future where humans don't need intelligence. In a few tens of thousands of years, human intelligence devolves. Then what's all this talk about interstellar colonization? Another great filter is the progress of scientific knowledge itself. You know, it's not a given that science must always advance. We just lived through the 20th century, a boom time for physics, so we feel like science will always advance at that breakneck speed. But think about it. After general relativity and quantum mechanics, have we had any major breakthroughs in fundamental science? No. It's possible that the development of science has stalled. Our fundamental science is locked. In 1900, Lord Kelvin said there were 2 dark clouds over physics. With the 20th century boom, those clouds dissipated. But today, our sky is full of dark clouds. The free parameters in the Standard Model, dark matter, dark energy, the origin of life, these are all dark clouds. Perhaps human knowledge has already hit its limit. We will never evolve into Type 2 or Type 3 civilizations. And perhaps aliens are just like us. Their knowledge is also locked. And so, they can't develop the ability to colonize the stars. Okay, let's circle back. What is the Great Filter hypothesis saying? Let's go back to the mind map. It's saying premise 1, principle of mediocrity, is correct. The universe can theoretically have alien civilizations. But premise 2 is wrong. Before an alien civilization can develop the ability to colonize, it is filtered out by one of these layers. In this sense, we humans, who are subject to the principle of mediocrity, are actually not so mediocre. We, by sheer luck, have passed the first 8 filters listed by Hansen. This is an incredibly low probability event in the context of the entire universe. Intuitively, the principle of mediocrity suggests that with a large enough sample size, even low probability events will happen. The universe is big enough and old enough, so someone must have gained the ability to colonize, right? Well, yes. But the problem is, while the universe's sample size is large, it's not infinite. The great filters make the probability of evolving a starfaring civilization so incredibly small, that even the 13.8 billion light-years of space and 13.8 billion years of time are still too small a sample size. That's what the Great Filter hypothesis is saying. Okay, after the Great Filter, let's introduce the self-destruction hypothesis. This one is a bit like the Great Filter, and it also falls under the can't come, lack the ability category. So how does the self-destruction hypothesis explain this lack of ability? It's because once the universe evolves intelligent life, intelligence itself is self-terminating. Intelligent civilization has an innate tendency towards self-destruction. Once a civilization develops intelligence, it won't be long before it plays itself to death. Of course, this has a technology as a threat vibe. We humans are very familiar with this. It's an old trope in sci-fi. As human technology advances, we find 1,000 ways to kill ourselves. For example, nuclear war. We blow up ourselves and every other plant and animal on the surface. Or the Large Hadron Collider creates some strangelet, which creates a black hole, which falls into the Earth's core and swallows the whole planet. Or biotechnology, like gene editing, where we edit ourselves into extinction. Or the development of AI, which loses control, enslaves, and finally exterminates us. And so on. We're all familiar with these sci-fi tropes. But let's introduce another, more innate logic for why intelligent civilization self-destructs, the light cage limit. What's the light cage limit? Simply put, it says that no starfaring civilization can exist. Because by the time a civilization needs to colonize the stars to relieve population pressure, it would have already destroyed itself. Specifically, once a civilization develops the ability to colonize, say, it reaches Type 2 or Type 3 levels, it will initially reap huge benefits from constant outward expansion. Starting from its home planet as a center, it expands via self-replicating AI probes. During this expansion, the colonizing population will also grow, and it will grow exponentially with the colonization progress. At first, within the sphere of its expanding territory, the population density remains constant. Why? Because the volume of colonized space is also expanding exponentially to match it. But one day, the speed of this spatial expansion will approach the speed of light. And once you hit the speed of light, the volume of your territory is caged. You cannot expand faster than light. When the civilization's expansion speed hits the speed of light, it hits the so-called light cage. At this point, the expansion of colonized space and resource acquisition grinds to a halt. But the exponential growth of the population doesn't stop. And at that moment, the entire civilization collapses. You might think it would take a very, very long time to reach the speed of light. But no. Because this is an exponential growth curve. Even if the population growth rate is only 1% at the start, a civilization with interstellar capability will hit the light cage in just a few thousand years. A few thousand years, on a cosmic scale, is the blink of an eye. This explains why we can't find them. Because as soon as a civilization gains the ability to colonize, it will hit the light cage within a few thousand years and destroy itself. So, the very ability to colonize has an innate, self-destructive tendency. It's like an interstellar Malthusian trap. Once you fall in, the civilization either goes extinct in a few thousand years, or it must maintain a low growth rate, give up on colonization, and live a low-carbon, stay-at-home lifestyle. Right? If they're all staying at home on their mother planet, of course we'll never find them. So, to summarize the self-destruction hypothesis, why haven't we found them? Because any civilization that reaches the technological level capable of colonization will fall into a self-destructive trap. So we can't find them. Okay, after self-destruction, let's introduce the estivation hypothesis. The estivation hypothesis also posits that when a civilization develops to a certain point, it hits a limit. But it's not self-destruction. The limit is that it must take a long nap before it can start colonization. What does this mean? Well, when a civilization has the capability for interstellar colonization, its energy consumption will be enormous. And such a high-tech civilization will surely be one that relies heavily on computation. This raises a problem. How do these energy-guzzling supercomputers dissipate heat? Right? Even if their computers aren't based on our Turing architecture, they still have to obey the laws of thermodynamics. They must dissipate heat. If the computer is too hot, it runs slowly. It's only efficient when it's running in a low-temperature environment. So, what can they do? They have to wait. Wait for the universe to cool down. Only then can the supercomputers needed for colonization run efficiently. We know the universe started from a single point, the Big Bang. The temperature at that point was extremely high. After the Big Bang, the universe has been constantly expanding. And this expansion process is also a cooling process. The current temperature of the cosmic microwave background radiation, the leftover heat from the Big Bang, is 2.7 Kelvin, which is minus 270.45 degrees Celsius. As the universe expands further, this temperature will drop even more. The aliens are just waiting for the universe to cool down further so they can turn on their supercomputers and begin colonization. This process of waiting for the universe to cool is called estivation, or summer hibernation. It's an apt metaphor. It's too hot in the summer, so you wait for cooler weather to get work done. During this period of estivation, the aliens are not engaged in colonization activities. This explains why we haven't found them. Because any civilization capable of colonization faces this heat dissipation problem. They are all currently summer napping, waiting for the universe to cool. That's the estivation hypothesis. Do you think it makes sense? Okay, after the estivation hypothesis, let's introduce the dark forest hypothesis. A quick programming note, our Ultimate Thought Experiment series is typically a philosopher's meeting to debate a big question. We don't just popularize views, we want to hear your thoughts. Do you think the views presented successfully answer the big question? Or do you have a better answer? We invite you to join the seminar with the philosophers and interact with us in the comments. Okay, let's continue. The 4 hypotheses we just covered were all in the can't come, lack the ability category. Next, we'll talk about those who have the ability, but deliberately remain silent. The most famous of these, of course, is the dark forest from Lutz Cixin's novel The Three-Body Problem. We all know what the dark forest hypothesis is. In our logic map, it says premise 1 is correct. The universe is full of intelligent civilizations with the ability to colonize. But premise 2 is wrong. These civilizations deliberately remain silent and do not announce their presence. Why? Precisely because the universe is full of them. This means the universe's resources have basically all been claimed. Resources are extremely limited. So, if my resources are discovered by another civilization, they will use violence to take them. So why not sit down, talk, and trade? Why must they resort to violence? Lutz Cixin uses game theory to explain this, the chain of suspicion. Communication between different starfaring civilizations is not smooth. Think about it, communication between different human races is already difficult, let alone between different species from different stars. Right? Therefore, when one civilization encounters another, even if there's no initial hostility, the difficulty of interspecies communication creates a problem. How do I know you aren't hostile? Even if I'm not hostile, how do I know you know I'm not hostile? Even if I know you know I'm not hostile, how do I know you know that you know I'm not hostile? Right? This chain of suspicion is endless. This chain makes interstellar communication impossible. So, when two civilizations meet, the most rational move is to strike first. Wipe them out and take their resources. This is what causes all civilizations in the universe to resort to violence. The universe is a dark forest that obeys the law of the jungle. The universe isn't about politeness, it's about killing. So, the dark forest law explains why, even if premise 1 is true, the universe is full of civilizations, it doesn't lead to proposition 1, that we should see them. Why does the universe show a great silence? Because every civilization in this dark forest, for its own survival, never sends out radio signals to reveal its position. They are all just listening, waiting for someone else to reveal their position. So, for every civilization, the rational strategy is do not answer. But we humans are the silly child in the forest. We keep sending signals into space. We're just waiting for aliens to come and exterminate us. As Lutz Cixin says in his novel, In the Dark Forest, there is a stupid child named humanity. He has built a fire and is shouting next to it, I'm here. I'm here. The physicist Stephen Hawking also said that if aliens visit us, the outcome would be much like when Columbus landed in America, which wasn't good news for the Native Americans. That's the dark forest hypothesis. Of course, some have criticized it. The main criticism is that the universe is vast and empty. The idea that it's already full of civilizations and all resources are claimed is questionable. Okay, after the dark forest, let's introduce the new tech tree hypothesis. We've covered can't come and won't come. Now let's introduce the don't need to come category. This is also a refutation of premise 2, which states that civilizations must expand. But does a highly advanced civilization have to follow the path of imperialism to sustain itself? Besides colonization, a civilization could just unlock a new tech tree to develop itself. The new tech tree hypothesis can be stated as a paradox. By the time a civilization is advanced enough to be capable of interstellar colonization, it no longer has any need for interstellar colonization. How can this be? We can imagine that when a civilization's technology reaches a certain point, it develops black technologies for highly efficient energy use. It can turn previously non-scarce materials into energy. For example, mastering controlled nuclear fusion, or antimatter, or harvesting energy from the quantum vacuum. Then you don't need to go to all the trouble of colonizing other planets. Right? It's like playing Warcraft 3, The Frozen Throne. Normally, you have to keep expanding to new bases because the gold in your main base is finite. But what if the mine in your base was a supermine? A gold mine with 999,999,999 gold in it, one that you could mine forever. Why would you ever expand? Let's go back. Premise 2, which says civilizations must expand, is actually a projection from our own technologically limited human perspective. This is a case of poverty limiting our imagination. It's like an ancient peasant imagining the king's life. The peasant uses an iron hoe every day, so he imagines the king must use a golden hoe. Right? We humans look at our own history, limited resources, must expand. Our ancestors expanded from Africa to the globe. Europeans followed the path of imperialism. So, we assume advanced aliens must also expand. This is purely projecting our own nature onto them. It's a human-centric error. By the same token, based on this human-centric bias, we look at our own situation. Almost all our energy comes from the sun. So, we assume an alien civilization must also have a star like the sun. And when they reach a certain stage, they must build a Dyson sphere to wrap it up. And when that energy isn't enough, they must colonize other systems and build more big projects. We always think a civilization must build a Dyson sphere, do big projects, and make big news for the whole universe to see. But who says big is good? Maybe a highly advanced civilization develops on the micro scale. Right? Maybe they just love playing with nanobots. Or they pull energy from the quantum vacuum. Can an advanced civilization follow a small is beautiful path? They don't have to expand. To avoid this human-centric bias, we must also recognize, any prediction you make about the future based on your current understanding is probably wrong. Because when you develop to a certain point, your understanding itself changes. Think about it. Our technology today is worlds apart from 200 years ago. A person from that time looking at us today would be looking at a different dimension. So, if we humans are still using the 200-year-old, outdated imperialist expansion model to predict our own future, that's just our poverty limiting our imagination. If 200 years can create such a cognitive gap, what about an alien civilization that's had tens of thousands, or millions, of years more than us? How can we possibly say that to develop, they must follow the path of colonization and aggression? Right? Okay, let's recap. The new tech tree hypothesis solves the paradox this way. By the time a civilization is advanced enough to be capable of colonization, its technology makes colonization unnecessary for its survival. After the new tech tree, let's introduce the Metaverse hypothesis. This one is similar to the last. When a civilization reaches a certain stage, its technology is beyond our comprehension. It's no longer following the low-level path of imperial expansion. The Metaverse hypothesis says that when a civilization gets advanced enough, it just enters the Metaverse. This means the civilization transitions from the physical world to a virtual one. Like in the movies The Matrix or Ready Player One. You just plug a tube into your head and log into a virtual world, or just upload your consciousness directly. At that point, everyone just lies at home and plays games. How great is that? Green, environmentally friendly, low energy. No more resource scarcity. Your waifus in the virtual world are wonderful. There's no need to be a tryhard and expand outward. Right? And just like that, the Fermi Paradox is solved. The more a civilization develops, the more it enters the virtual world. This isn't to say the civilization degenerates. It's that as it develops, biological civilization enters a post-biological stage. What does that mean? Let's use humans as an example. At our current level, we think the carrier of civilization is the gene, passing on our species' genes by having children. But as civilization advances, the carrier of civilization will shift from the gene to the meme, or culture. So, as long as the culture being transmitted is human culture, then it doesn't matter what the physical substrate is. Whether it's a carbon-based biological body or a silicon-based computer hardware, it's still human civilization. So, when a civilization enters its post-biological phase, to advance that civilization, replicating memes in a metaverse program is far more efficient than making babies with physical bodies. Right? In this sense, in a highly advanced civilization, AI robots become the physical carriers, or there's no physical body at all. They achieve mechanical ascension or just upload consciousness. They only need to transmit their memes within the metaverse. This is the Metaverse hypothesis's solution. Why haven't we found advanced alien civilizations? Because they are all living in the metaverse. Okay, after the Metaverse hypothesis, we come to the final possibility for solving the Fermi Paradox. They don't exist. As we said, there are three main possibilities. Proposition 2 is false. Premise 2 is false. Or premise 1 is false. We've covered the first two. Now for the third. There are no aliens. In the entire universe, human civilization is the one and only. Now, if we are the only intelligent civilization in the universe, we must answer the question, why are we special? This third possibility is a rejection of premise 1, the principle of mediocrity. It says, we are not mediocre. We are different. So, we must explain why we are different. The answer depends on how you reject the principle of mediocrity. There is a weak rejection and a strong rejection. The weak rejection is a probabilistic rejection. It says that, fundamentally, we humans aren't special. We are, at our core, mediocre. We theoretically evolved according to the same physical laws as everything else. It's just that, technically, evolving an intelligent civilization is extremely difficult. The probability is just too low. And that's what makes us special. The strong rejection says it's not just technically difficult, it's theoretically impossible. Evolution cannot produce human civilization. Okay, let's talk about the weak rejection first. Paleontologist Peter Ward and astronomer Donald Brownlee proposed a hypothesis called the rare earth hypothesis. Rare earth, as the name implies, means that a planet like Earth, one that can evolve a civilization like ours, is extremely rare and special. How special? First, the Sun. We know you need a stable, burning star for life. This means the star's mass can't be too large or too small. Why? We know Earth needed about 1 billion years to cool down enough for life. Another billion to form the oceans and atmosphere. And another 2 billion to get from single-celled life to intelligent life like us. That's almost 5 billion years, all of which requires a stable, burning star. This stable burning phase is called the main sequence. Our Sun's mass gives it a 10 billion year main sequence lifespan. And it has currently been burning stably for exactly 5 billion years. If a star is too massive, its nuclear fusion burns faster. For example, one of the closest stars, Sirius, is twice the mass of the Sun. Its main sequence life is only about 500 million years. You can't hope to find aliens in the Sirius system. So, you say, just find a less massive star, right? It will last longer. Ah, but it can't be too small. If the star is too small, it doesn't give off enough heat. The planet would have to orbit much closer to get enough warmth. And if it's too close, it becomes tidally locked. This means its rotation period is the same as its orbital period. The planet always shows the same face to its star. Just like our moon is tidally locked to Earth. This would make one side of the planet a permanent, scorching day, and the other side a permanent, freezing night. The planet would be a world of fire and ice. So, the star's mass can't be too large or too small. Our Sun's mass is in that perfect, just right range. Okay, now Earth. Earth's distance from the Sun is not too far, not too close. This allows for an average surface temperature of about 20 degrees Celsius, permitting liquid water. Look at our solar system. Venus, slightly closer to the Sun, has an average surface temperature of 500 degrees Celsius. All its water evaporated. Mars, slightly farther away, has an average temperature of minus 55 degrees Celsius. Forget liquid water, its carbon dioxide is frozen as dry ice. Okay, now Earth's surface area. If it were slightly larger, it would radiate heat too quickly, making the nights extremely cold. If it were slightly smaller, it couldn't dissipate enough heat, and the planet would get hotter and hotter. Now, Earth's mass. If it were slightly lighter, its gravity would be too weak, and its atmosphere would become thin or disappear entirely. If it were slightly heavier, it would attract more greenhouse gases like carbon dioxide. This would cause the surface temperature to rise, turning it into a hothouse planet like Venus. Of course, the list of Earth's special conditions is too long to list. The 23.5 degree axial tilt. The fact that its orbit is almost a perfect circle. And if you get into biology, the asteroid that wiped out the dinosaurs, making room for us, the humidification of the East African savanna, allowing our ancestors to migrate. The list of special conditions that allowed for the evolution of a civilization like ours, you could write 10 books and not finish. We're just listing a few so you get the idea of what an incredible stroke of luck our evolution was. And note, these countless special conditions are not just additive. They are multiplicative, one link to the next. If you miss any single link in the chain, you don't get life, let alone intelligent life. So, let's go back. Even though we said at the start that, Theoretically, if the universe can make us, it can make others. Yes, it's theoretically possible. But it's technically so difficult. You have to get all those interlocking conditions just right. And to get all those conditions right? I'm sorry, but even with the entire universe of 13.8 billion light-years and 13.8 billion years as your sample size, it's still too small. In that small sample, we, Earth, are the only ones who, by chance, got them all right. So, the rare Earth hypothesis, in this sense, is similar to the Great Filter hypothesis. The Great Filter says there are hurdles. The rare Earth hypothesis emphasizes the uniqueness of Earth, as the only one, so far, to have passed all the filters. We are the only intelligent civilization that has evolved in the entire universe. Okay, that's the rare Earth hypothesis. It's the weak rejection of the principle of mediocrity. Next, let's introduce the strong rejection of the principle of mediocrity, the creationism hypothesis. The strong rejection of premise 1 says we are different. Why? Because we are the chosen ones. Right? This solves the Fermi Paradox easily. Why haven't we found aliens? Because intelligent life, or even life itself, cannot arise from evolution. It must be created. By whom? And how? That's another big question. We've talked about that in previous episodes, so we won't go into detail here. But in the context of the Fermi Paradox, if we say we were created, it seems to solve the paradox, but it just creates a new paradox. How? If we were created, that implies the existence of a creator, a higher intelligence. And that implies the existence of aliens. This is a new paradox, isn't it? On the one hand, you deny the principle of mediocrity and say there are no aliens. On the other, you say we were created by a higher intelligence, which means there are aliens. So, are there or aren't there? Well, to solve this new paradox, we could say that the higher intelligence that created us isn't in our dimension or universe. They are in a parallel universe. We could call them outsiders, from an outside universe. When the outsiders created us, they created our entire universe along with us. So, while the outsiders exist, within our dimension, our universe, we are still the only intelligent life. And that solves the new paradox. Right? But this just leads to another paradox. Who created the outsiders' universe? This brings us back to the infinite regress problem we talked about in our episode about whether you can kill your grandfather. And that problem never ends. If you're interested, you can check out that episode. We won't repeat it here. Okay, that's all the solutions to the Fermi Paradox we'll introduce. Let's move to the summary. In this episode, we shared 13 solutions to the Fermi Paradox. The paradox exists because of two contradictory propositions. Proposition 2 is a fact. Proposition 1 is a high-confidence deduction, based on two premises we believe are true. To solve it, either Proposition 1 is false or Proposition 2 is false. If Proposition 2 is false, it means aliens have already contacted us. This leads to the UFO hypothesis, the lizard people hypothesis, the zoo hypothesis, and the panspermia hypothesis. If Proposition 1 is false, it means either Premise 1 or Premise 2 is false. If Premise 2 is false, it means aliens exist but haven't contacted us. This leads to several possibilities. They can't come, the too far hypothesis, the Great Filter hypothesis, the self-destruction hypothesis, and the estivation hypothesis. They won't come, the dark forest hypothesis. They don't need to come, the new tech tree hypothesis and the Metaverse hypothesis. If Premise 1, the principle of mediocrity, is false, it means there are no aliens. The weak rejection gives us the rare Earth hypothesis. The strong rejection gives us the creationism hypothesis. Of all these 3 possibilities and 13 hypotheses we introduced today, and using the 5 criteria for reasonableness, which one, or which ones, do you find most reasonable? Or, if you have a hypothesis you find more reasonable, please share it. Finally, I'll share my own thoughts. I remember watching a video of Lutz Cixin, the author of The Three-Body Problem, in an interview. He was asked, the fact that we haven't found aliens, is it because they are too primitive, or because they are too advanced? Lutz Cixin replied that neither of those conclusions is very shocking. The truly shocking conclusion is, it's very possible that we are, in fact, the only civilization in the entire universe. Why is this conclusion shocking? Let's not debate whether aliens factually exist or not, that's what we're here to discuss. But regardless of our conclusion, in our hearts, we already have an answer we want to be true, that aliens do exist. Why? Because we fear loneliness. We are afraid that in this vast, boundless universe, we are utterly alone. That our appearance here has no reason, that it's just a cold, random accident. We appeared for no reason, out of nowhere. We will disappear for no reason. And if no one else ever saw that we were here, it's as if we were never here at all. The Czech writer Milan Kundera, in his novel The Unbearable Lightness of Being, mentioned a German proverb, einmal ist keinmal. Translated, it means once doesn't count. What happens only once might as well not have happened at all. By the same token, if we are the only civilization in this universe, our existence is like non-existence. Our existence is void. We're like a wild lily blooming in the mountains. It blooms and wilts, all by itself. If no one ever sees it, was the beauty it displayed when it bloomed still beauty? Our existence, the radiance we give off, longs for a witness. Because only by being witnessed does our radiance become beautiful. Only then does our existence have meaning. And to be witnessed, you need the other. The self's reality, and the world's reality, is guaranteed by the other. If no one else exists in this world, if there's only one big I, then I fall into solipsism. I start to doubt if the world is just my own fantasy. Am I living in the Truman Show? Or the Matrix? Everything I experience is just a set, or a simulation. I even start to doubt my own existence. Maybe I'm just a brain in a vat. The world I experience, the self I experience, is just a dream, a phantom bubble. In this sense, aliens are our other. We need them to exist. Otherwise, if it's just us, how can we be sure we are real? How can we be sure our existence is not a void? This is why, even though contacting aliens carries risk, the humans in the three-body problem are still like that silly child, building a fire and shouting, "We are here. We are here. Because we were here. And we will, eventually, be gone. We just want someone to remember we were here." I think this might be the underlying reason why we are so fascinated by the question of aliens. Every time we look up at the starry sky, perhaps we are hoping that, on the other side of that sky, a pair of eyes, the eyes of the other, are looking back at our lonely selves. Of course, hoping they exist is one thing. Whether they exist is another. And that is what we are here to discuss. Today, I've shared some hypotheses about the existence of aliens. Now, it's your turn to speak. Please comment below. Okay, that's all for today. Thank you for watching and for your company. Feel free to like, subscribe, and share. Good night, my friends.